Hey guys, welcome back to episode number 5, but this is more like the continuation for episode number 4, where we did our first uh, diffuse material. But however, when we come into the render scene, we have this mess, this low quality, low resolution mess, um, low resolution mesh, mesh, mess. Okay, we have this low resolution mess. We need to correct this. Obviously, in the last episode, I said at the end we need to add some anti-aliasing. So that's what we'll be doing today, and you won't believe how much of a difference it makes when we add anti-aliasing. So let's come back. I have only 30 minutes recording time in my phone because my storage space is always running out. So let's actually be quick here. So the first thing we need to do is come into our ray tracer CPP, and let's actually define a function. So let's come down here and say we need um, a square, so a position, so f vector, and I'm going to call this f vector uh, pixel sample square, and it's going to return an f vector. So let's create a definition. God. So there you go, and let's create an auto px. So minus 0.5 plus our ray utility. So we need our ray utilities as well. So make sure you have included ray utilities in our header file, and then come to our instances. Let's actually create a ray utilities pointer, ray utils, and then come back to our CPP, and then let's declare our object or create an object of ray utilities. So ray utilities is equal to new object, and then we'll call that a ray utilities, right? So that's pretty much it. Let's come down quickly and add ray utils get random double in range 0 and 1. So the theory goes like this, right? So I'm actually going to cover a little bit of theory as well. So what happens in anti-aliasing? So there's this famous quote by someone, I don't remember their name, but it says a pixel is not a square. So the computer physical pixel is actually a square, but when we think about the color values of a pixel, it's actually not a square. So in anti-aliasing, what we actually do, anti-aliasing, anti-aliasing, what we actually do is for a single physical pixel, we don't shoot the ray straight through it and calculate the return point or the return value, use the return value, sorry. Instead, we actually take a square around the pixel. So we have a square and we have a pixel at the center. So this is the pixel. We actually take the square around the pixel, and then we take samples in that square around the pixel and shoot rays through those samples, and then add the colors on top of it. So that's why we say a pixel is not just a square, it's the points around the pixel. So we add the values, so we have that smoothing effect. So colors are not now in a range between 1 and 0, for example. It'll be all the values around those pixel added up. So what that means effectively is you won't have sharp edges, you'll have smoothed out colors. That's what we're trying to do. And in our ray tracer right now, we have those shadows as point, point, point. But when we do anti-aliasing, we'll have that smoothed out shadows and edges, of course. So that's what we're doing here. We're calculating the points around the pixel. We'll actually add the pixel location later. So let's do py as well. Minus 0 0.5 plus ray utils again. If you guys don't understand anything I'm saying, if you guys have doubts and stuff, do let me know in the comments below. Or you can actually read Peter Shirley's book with some brief explanations and diagrams, obviously. And the last thing we want to do is return px multiplied by pixel delta u, and that's why we actually declared it in the global context, py multiplied by pixel delta, so pixel delta v, right? So now we have an f vector, or the locations around our pixel value. So let's come back to our for loop, so our render loop. At this point we call it the render loop, and come to and write another loop, pretty much, int s is equal to 0 and s is less than a sample count and s plus plus, right? The sample count, again, we should come back to our header file and define it as a u property integer. So integer u property, come down here and just say sample count. I'm trying to be quick here because my time is running out. I mean the recording time. I still have a lot of time. 10. So now what it means for a single pixel, we'll shoot 10 rays around the pixel and calculate their color and add it up to that single physical pixel's value. So we get that smoothing effect. So we have the sample count ready. Now what we want to do is actually the pixel location. I think it's a pixel location, I have no idea. So the pixel sample, I think we'll name it pixel sample is equal to pixel center plus our pixel square sample square. So we have a pixel location, so that's what I said about the calculations we did earlier on for just a single pixel, and then we add the samples around the pixel, so we get new locations around the pixel, right? So let's do that, and we'll also have to change our direction. So let's copy this, and instead of that, we're actually going to put pixel sample minus look from, so that's our new direction. And I think that's pretty much it. Let's actually create a new vector, f vector, and let's call it color vector. Initialize it to 0, 0, 0, and that's pretty much it. So now we can actually call the ray color function from here. So instead of just calling it, we'll actually add it, right? So plus equals sorry, plus equals color ray color, and we can copy this and put it here. So now instead of just shooting one ray per pixel, instead of shooting one ray per pixel, we are shooting the sample count amount. So right now it's default at 10. You could reduce or increase it. And I think this is a good point to advise for low-end computers. The pixel, the sample count is actually a big factor in slowing down your render time. So if you have a lower pixel count, the faster the render is. If you have a higher pixel count like 100, it's actually going to take some time, and with higher resolutions it's going to be a long time before you see an image on the screen. So in your debugging process, it's better to keep your sample count down. And if you have lower end computers, it's better to work with a lower sample count. So that's what I like about building your own ray tracer, because you have that minute control, that lower end control. So keep that in mind. So now we have our color values and color vectors. Now if I try to play this, you might see that we have a problem. So let me actually quickly build this to see we don't have any errors, to make sure we don't have any logical errors as well, but it's doing fine. So let's actually run this. So yeah, it's taking quite enough time, and we get this, a big mess. And the reason for that is, come back to YouTube ray tracing, is the value we are adding on top and top and top and top. So If we have a color vector set to 0, 0, 0, and we have 10 sample counts, and we, like, let's say this first ray returns a color value of 100, 100, 100. So now we're adding 100, 100, 100. But the color value is clamped to a range between 0 and 255. So we have to rectify that. So when the sample count increases, we'll eventually break that point of 255 and go into 300, 400, even thousands. So keep that in mind. So we have to change that, and the way we do that is a little bit unnecessary, or not unnecessary, it's necessary, but it's kind of you can just copy paste the code if you're following along, because it really doesn't hold any real value, I should say. Not, I think I'm phrasing all this wrong. Value, I think it calls for automation. That's what I'm, no, forget it, guys. Let's just code it by hand. The point I'm trying to say is you don't have to code it by hand because it's really time consuming, and let's just do it, guys. Let's just do it. Okay, let's code it by hand. First we need to get the X and Y and Z components, so the RGB components. So let's actually do auto R and get the color vector dot X, auto G, color vector dot Y. So this is the point I mentioned earlier in the last episode, that you could actually return F color instead of doing yourself and accessing vector values. But it really doesn't have a change, because if you have to do RGB, then you would simply call R, G, and B. It's all vector classes, so it doesn't matter. Then we actually need to int size, calculate the size of 1 divided over sample count, which will be multiplying, actually I think it's float or integer, I don't know. Let's just put float for now, because sample count and 1 divide, I think it's float. So now what we want to do is multiply all these values by the size. I think this is what I was trying to say. There's a lot of repetition. Okay, the code is having a lot of repetition. That's what I said. You can just copy paste the code. It does hold value. As you will see, it'll have a lot of changes, day and night changes to our render. Repetition is the word. Okay, word of the day, repetition. So we have RGB calculated. The next thing we want to do is actually divide all this again by 255. So R divide equals 255. The reason why I'm doing it, because the max range is 255. So we'll do that. I'm not entirely sure I remember this part well, so I might have to recheck with my old code. So RGB, and after all this is done, we actually need to get the power of certain values. So I think it's R to power of R to let me actually quickly check this out. R to power of, so auto scale, okay, so I'm just gonna copy that, rather not, but it's actually 1 by gamma, so 1 divided by gamma, and gamma, let's actually define gamma in our area here. So let's actually put u property, okay, not u, primitive component, okay, edit anywhere, and then come down and say float gamma. I'm going to put it at 3 for now, or maybe even 2. So gamma is going to be the brightness component, or the variable that controls brightness. So gamma is going to be here, and we'll just say the rest, power g 1 over gamma, bam, b power be 1 over, okay, not multiplication, well, 1 over gamma. So we're not done yet. We just have to add this line of code. So we're casting it into int. So now we are in our auto RGB is going to be actually in a double value or a float value. This is actually called scale, but I'm going to keep the size here. And we're multiplying it within a range of 0 to 1. That's pretty much it. So let's copy this and Control V, G, G, and B. So now we can just put this as G. If I can click it, we also have an alpha value, so the transparency, but we don't have to worry about it because it's always going to be 1 or 255. So we can actually see the image on the screen. So that's pretty much it, other than us assigning the color value as R, G, and B. So I think that should work. The line of code here, actually I'm quite confused at what it does actually. So we're actually taking the range between 0 and 1 and multiplying it by 255. I mean, that's fine because we're dividing it here by 255. So it should be less than the range of 0 to 255. But I don't know why we're clamping it here. Maybe it's not in the 0 to 1 range. I'm not sure, but let's actually build this and check if you have any issues. Also, if you guys have any better solution to do all this, I would be actually very happy to know. So let me know in the comments below, because I think this is just too much code for I think I'm missing something here. I think I'm doing one thing twice. I'm repeating something and I can't. I think it's the division, because we already have the vector value between 255 and 0 and 255. I don't know why we have to divide it and then multiply it again. So I think this should be, I don't know, I have no idea, guys. So if you guys have a better solution, do let me know in the comments below. I was just experimenting and got this solution. So let's come back and check if we have a good response. Okay, so there we have it, our first official ray traced image. So now we can see the shadows are much more smoothed out and we don't have that jagged lines in the horizon. We still have jagged lines in the mesh. As I mentioned earlier, this is a side effect of using meshes in our line tracing. You could do mathematical sphere intersections, but for now I think this works pretty well. So if I put down our gamma value, which is 2, if I put it to 1, we'll see the image get a lot darker. So this is what it gets, and we can see more pronounced shadows. And if I increase the sample count, let's say I'll put a 30, we'll see a much smoother image. Yeah, so now we have less splotchy areas and much more cohesive coloring. So let's just close that and increase our resolution to 1000. So this is going to take some time, and my CPU is actually getting hot. Let me actually see the temperature of my CPU. I think it should be quite hot. Yeah, it's okay, it's fine. It's at 65 degrees right now, but it is taking a lot of time to render. So let's wait, and our temperature is going 66. So the max was about, what is the max? 66 degrees. So it's it's pretty good, but we're doing simple calculations here. So we can see we have our first beautiful ray trace image. Actually, this is our diffuse material with anti-aliasing, and we have officially created our first ray traced sphere. Now, as I mentioned, we still have those lines. If you have a solution to fix that other than increasing the poly count in a sphere or any model, actually, do let me know in the comments below. One thing we can do, actually, I have a little more time in recording, so the advantage I'm going to show you, we have seen the disadvantage of using line traces or raycast. The advantage, however, is I could pretty much drag any mesh I want. So let me go to programming. Not programming. I think it's in. Yeah, I have Blender Suzanne monkey. I'm just going to import that. So I have Suzanne here. What I can do is come to blueprints and create another hittable object. Hittable, select, and I'm going to call this hittable monkey, and come to hittable monkey and add a static mesh and add to the root, and I'm going to call it my Suzanne monkey. There you go. Reduce the size, actually it's quite big. So I have my hittable monkey here. So let's actually take the hittable monkey, not the Suzanne monkey actually. Go to blueprints, hittable monkey, and then put it right there. And let's see how that works out. Also, to make sure it's in diffuse, let's actually bring down the sample count for this one because I don't think it's necessary, and the resolution as well. So 500 I think is much fine. So let's just render it out. Okay, so immediately we have a problem. We have a low poly model of Suzanne monkey, and that's because we have we're not actually using the complex mesh. So let's actually go and fix this really quickly. Go to your static mesh, and in here, if you see our collision, let's remove collision, and let's do this one, apply collision, and this collision is what we are seeing in the ray tracer. So the light hits the collision rather than the mesh itself. So let's come back to, that's one disadvantage actually, another disadvantage of using line traces. But we can fix this. Actually come to our collision, and then here we can actually use project default and use complex as simple. So this is going to be our collision now. So let's actually save this and come back and try this out. Yeah, so now we have our Suzanne monkey, the complex collision as simple. So that's pretty much it for this episode, anti-aliasing and complex meshes, right? In the next episode, we'll be actually implementing reflect functions for metal material, and also hopefully refract functions for glass material. So that's pretty much it for this video. If you guys enjoyed the video, make sure to leave a like and consider subscribing, and also consider supporting me on Patreon. You'll get access to project files and source codes, and I'm also planning to put out some extra content. So with that said, I will see you guys in the next video. Bye bye.